Hey everybody. Today we're getting into the first fundamental theorem of calculus. As you might guess from the name, it's a pretty important theorem. That's true not just from the theoretical perspective, but also from the practical perspective of just trying to get problems done. So this whole conversation is based on the idea of an accumulation function. We have this graph, y equals f of t, and we're defining a new function by the area under that graph from some fixed starting point, t equals a. Here I've drawn it with t equals 4, and some variable ending point t equals x. So as x gets larger, you accumulate more area. And if the graph is above the horizontal axis, you're going to be accumulating positive area. And when the graph is below that horizontal axis, you'll be accumulating negative area. So it seems, at least visually, that the function f of t is a derivative of the accumulation function. Or to say it differently, the accumulation function is an antiderivative of f of t. And in fact, that's the case. The theorem is the first fundamental theorem of calculus, and it says that if you have a continuous function, f of t, on some interval, then that accumulation function is differentiable, and its derivative is just the function on the inside. Let's rewrite this in a slightly more compact form. This is really suggestive. It just says that if you differentiate an integral in the proper sense, you get the original function back. The derivative of an integral is the original function. Now, you have to be careful when you say something that efficiently because we're differentiating an integral in a very specific sense, in the sense of an accumulation function. Let's actually go through the justification here. Not quite a proof, but a justification at least, because I think it's actually enlightening to see this, unlike some proofs that are just more formal. Also, it's going to give us a chance to review our limit definition of the derivative. So we want to do g prime of x. We're going to be differentiating this accumulation function. Remember the definition of the derivative. The limit as h goes to 0 of the function evaluated at x plus h minus the function evaluated at x divided by h. Now, the numerator here on the right is really suggestive. We have the same function being integrated over two different intervals. So we can simplify that numerator using properties of the definite integral. We get the limit as h goes to 0, 1 over h, integral from x to x plus h, f of t dt. Here, I think a picture is helpful. We have this function y equals f of t, and we want to be integrating it from x to x plus h. So we're just talking about that shaded region on the far right, the light gray region. Now, that light gray region is, when h is small at least, approximately a rectangle. And therefore its area is approximately h times f of x, where x is the t value that we're at. So that derivative that we're trying to compute can be written, at least approximately, as the limit as h goes to 0, 1 over h, times the area of that rectangle, h f of x. Now those h's cancel, and I'm just left with f of x. So the derivative of that accumulation function really is just the integrand f. It's a fact from elementary real analysis that this is an equality. As h goes to 0, we don't need to worry about that in Calculus 1. Two quick examples. The computations with the first fundamental theorem of calculus to start off with are very, very simple, because in a problem like this, derivative of the integral from 3 to x sine of t squared dt is just evaluated by literally taking that variable in the upper limit of integration and plugging it into the function. So instead of sine of t squared, we get sine of x squared. One more. Derivative of the integral from 0 to x, t over 1 plus t cubed. Just take that x, pop it into the function, x over 1 plus x cubed. Not too hard.